Good evening, Internet. I am Matt Buyak, and in this video we'll be talking about Pascal's triangle, binomial coefficients, and the 15th problem from the Project Euler problem archive. So in the last video, we took a look at this problem and solved it using C and C++ and standard programming techniques. But I also showed very briefly an approach that could be used to solve this problem using analysis alone. And it took me under 30 seconds to solve the problem. But I didn't really go into any detail as to how that approach worked, why it was correct, or how I came to that. And so that's what this video is going to focus on. So just real quick to recap, this problem asks us to find the number of routes through a square grid starting at the top left corner and moving to the bottom right corner, following the grid lines and only moving to the right and down. And as part of our solution last time, we made the key observation that the only way to reach a particular intersection is going to be to approach it from the north or to approach it from the west. And so the number of routes to a particular intersection must be the number of routes to the intersection to the north plus the number of routes to the intersection to the west. And this is the insight that we built our solution on last time. Now, in order to proceed with our analysis approach, often when trying to tackle a math problem that it's not entirely clear how it should be solved or what the first step should be, sometimes a good approach is just to collect some data. And so that's what we're going to do now. Using our program from last time, we're going to get ourselves some data. So let's open up our problem 15, main.cpp. Oops. Okay. Let's trim this back to just 11 columns and 11 rows. Let's go down here, and as we're filling up our table, let's print out the value in each row and column. So we'll say here printf, let's see, %8lu. The 8 should just be to make it aligned to an 8-character boundary. So we'll say %8lu. We'll want to do this after we actually fill in the value. And we'll say cache row column. We'll also need to do that here at the beginning of the row. Oh, I need to put a... No, that should be fine. That should be fine. Okay, so we'll just do the same up here. Except this is going to be 0. And this is going to be 0. Okay. We need to be sure at the end of each row to add a new line. Okay. All right, let's switch this to a view like that. Okay. It's a little curious that we somehow lost the the top right corner of our grid there. But in any case, this is our solution. So the table here is just indicating how many routes will arrive at a certain grid intersection. If you imagine a grid of city streets, say, overlaid on top of this table, then this is the number of routes to each intersection. Okay, so now we have our data, and perhaps some of you are already making some connections. But if not, I want to introduce the next key concept in our solution, and that is Pascal's triangle. So let me open up our analysis file. Our analysis file does not exist. We'll make it. Okay, so Pascal's triangle, as it's usually presented, is as follows. You'll have the first row has a single 1. The second row is going to have 2 1s offset from the first row like so. The next row is going to be a 1, a 2, and a 1. And every subsequent row is going to be offset in a similar manner, but with each element being the sum of the 2 elements above it to the left and above it to the right. So you can see this 2 is the sum of that 1 and that 1. And if we continue in a similar fashion, we'll have 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. Let me just we'll just label this here. Oh, that's annoying. Put that back. Pascal's triangle. Okay, and if we go back to let's go back to our full screen view here. So if we switch back to our output, and you take a look not at the rows or columns, but at the diagonals, I think you will find a familiar pattern. So in the top left here, in this first diagonal, you have just a single 1. In the next diagonal, you have a 1, and then over here also a 1. In the third diagonal, you have 1, 2, 1. In the fourth diagonal, you have 1, 3, 3, 1, and you'll see that this matches Pascal's triangle. If we go back to Pascal's triangle here, the only difference is that it's turned kind of on its side. Great. So now we've connected our problem with a standard mathematical concept, which means that all the tools that might be available to understand Pascal's triangle, now we can apply to our problem. Okay, so the next thing that we need to talk about is binomial coefficients. So what is that? Let's start with a simple expression here, 1 plus x raised to the nth power, where n is some natural number. So let's start with, we'll say if n equals 0, then that's just going to be, our expression here is just going to be 1. If n equals 1, then it's going to be 1 plus x. If it's 2, then it's going to be 1 plus x times 1 plus x. And this may be starting to push the limits of your memory in terms of high school algebra, or perhaps not. But in any case, you may recall that we can distribute this number to each of the numbers inside this sum here. So we can write 1 plus x times 1 plus 1 plus x times x. And then likewise, we can distribute these inside this sum, and this inside this sum, and that will give us 1 times 1 plus x times 1 plus 1 times x plus x times x. Or as it might more commonly be written, x squared plus 2x plus 1. Okay, great. Let's continue. If n is equal to 3, we have 1 plus x times 1 plus x times 1 plus x. But we've already evaluated this first part here. And so we can say 1 plus x times our expression right here. And again, we can distribute this expression over 1 plus x, and so that will give us 1 times this expression plus x times this expression, which is equal to x squared plus 2x plus 1 plus x cubed plus 2x squared plus x. And that's all going to be equal to x cubed plus 3x squared plus 3x plus 1. And you might be wondering, where am I going with this? I'm just calculating these powers of 1 plus x with no real rhyme or reason. But if you look at the coefficients on each of these expressions, you may again recognize a familiar pattern and realize why these are called binomial coefficients and why they relate to Pascal's triangle. So in the first, in the n equals 0 case here, it's equal to, as the coefficient 1. Here we have the coefficients 1 and 1. Here we have the coefficients 1 and 2 and 1. Here we have the coefficients 1 and 3 and 3 and 1. And again, you'll notice that this matches Pascal's triangle. Here's that same 1, 3, 3, 1 pattern. And if you were so inclined, we could spend a lot more time proving that each of these patterns actually hold, that our problem solution it is indeed equivalent to Pascal's triangle, and that the binomial coefficients here are indeed equivalent to Pascal's triangle. In case that isn't obvious why that's the case, it is possible to go into a more rigorous proof. But I'm going to leave that as an exercise to the viewer. Okay, so it may seem like we haven't actually made that much progress toward our solution. We've collected some data, we've introduced some new concepts, but we haven't really made significant progress. But it turns out that binomial coefficients are ubiquitous in mathematics. They come up all over the place. And so, of course, there's an expression for them, and many of their properties are well understood. And so let's just suppose that we want to have this function f that's going to tell us a particular binomial coefficient. And let's say we'll say f of r comma e, and that's going to be for a particular row and element of Pascal's triangle. I'm just going to write now the expression, and then I'll explain what it is and how it is to be used. And so it's just going to be r factorial over e factorial times r minus e factorial. Okay, so first of all, if you're not familiar with this notation, with the exclamation mark, that's pronounced, r factorial. And just as an example for how that works, 5 factorial is going to be equal to 5 times 4 times 3 times 2 times 1. So n factorial is just going to be the product of the first n natural numbers. And so that's how the binomial coefficients are described. Now, one point of caution, you may notice if you actually start plugging in numbers here and trying to determine coefficients in Pascal's triangle, that something seems a little bit off. And in fact, in order to get everything to work out correctly, you can't number this row 1. You have to number it row 0 in order for the math to work out. And likewise, this diagonal here of the ones, you can't number that you can't number those element 1. You have to number them element 0. And you might wonder, why don't we just change the expression down here and make this r minus 1 factorial and make this e minus 1 factorial, etc. And you could do that. It makes this expression a little bit less clean. But the other reason is that it doesn't match up as nicely with other uses of the binomial coefficients. In particular, you'll recall that this first row here, or row number 0, corresponds to 1 plus x to the 0th power. And the next row here, the row that we've numbered row number 1, corresponds to 1 plus x to the 1st power. And so everything matches up if you number it as I've described. Okay. So the next thing is that this function is not referred to as f. Typically, the notation that's usually used to describe binomial coefficients, unfortunately, I can't easily show you in my text editor. So I'm just going to pull up good old MS Paint here and do a little bit of artwork. So if we, let's just grab a nice fat brush size. So the way binomial coefficients are usually, that's not a nice fat brush size. Let's see. Okay, there we go. Okay, so typically you'll see something like this: 2 large parentheses with some integer over some other integer, and that will be pronounced r choose e in this case. Another notation that you might see sometimes. Let's see if I go here. Let's crank up the font size here. So we'll say it's like 72. Make a nice big C, and then we'll make a couple of small. Make it like size 28. We'll make an R and an E there. Oops, we want transparent. Okay. The other notation you might see is something like this, where you have a little r preceding a big C, and then a little e after the big C, and that's pronounced r choose e. So you might wonder why choose? Why is that the pronunciation of these? And it has to do with the use of binomial coefficients in combinatorics and probability. So in particular, if we wanted to know, how many 5-card poker hands in a 52-card deck. And then the answer is going to be, 52 choose 5 is going to be the answer to that question. And so, similarly up here, this is not going to be f. I'm going to use this function choose. That's the notation that I'm going to use to describe the binomial coefficients. Okay, so now we're familiar with binomial coefficients. We have an expression for them. We understand how they relate to Pascal's triangle. We understand how Pascal's triangle relates to our problem. We're getting pretty close to being able to solve our problem. And in particular, you might plug our problem into this expression and come to the conclusion that the number of routes through a square of size n is choose, and this is going to be 2n factorial comma, or excuse me, 2n comma n squared. No, excuse me, it's going to be 2n choose n, which is equal to 2n factorial over n factorial squared. I was getting a little ahead of myself there and combining the two different expressions. But yes, that should be what we want there. And these are the central binomial coefficients. I briefly mentioned that term in the last video, and so this is where that comes from. And so you might think at this point that it's just simple enough. You pull up your calculator there, and we punch in 40 factorial, and then we divide it by 20 factorial squared, and it does indeed give us the right answer. But on many calculators, this wouldn't work. And the reason is that when you do 40 factorial, it turns out that on this calculator, on Windows 10, which is what I'm using, it keeps the full precision of this integer value. But many calculators, both physical calculators and software implementations of calculators, will truncate this after some number of digits. Like this expression here, 8 point some decimal times 10 to the 47th, it might only retain this many significant figures, which would not be enough for our purposes. We actually need all the significant figures in order for this to work out. And so it's fortunate that our calculator here is capable enough that we're able to calculate our answer. But that might not always be the case. Depending on the situation, maybe you're in some sort of mathematics competition. Maybe you just don't have a calculator on hand. You're just sitting there with your notebook and pencil and paper. How would we simplify this by hand to something that's a little bit more manageable? So obviously you could write out, 40 times 39 times 39 times 38 times ... divided by, 20 times 19 times 18 times ... etc. And go through and find, cancellations that you can do until you come to an answer. And that would work. It's a little bit tedious. And it doesn't necessarily provide any additional insight. And so I wanted to take an approach that I think will maybe grant a little bit more additional insight in addition to being a little bit cleaner. So the observation that I would make is that this has to be an integer value. All binomial coefficients are integer values. And so we know that all we have to do is figure out, what's remaining after we've divided this out. And in particular, we can do this per prime. That is, we might take the first prime 2 and look at how many times does 2 divide 2n factorial. And then look at how many times does 2 divide n factorial squared. And subtract one from the other, and that gives us the exponent of 2 in the prime factorization of our answer. And so in this way, we can avoid having to multiply out all of these, this long expression here and going through this tedious process of cancellation. And so I want to introduce just a little bit of notation that I think will be useful. I'm just going to call it mult LTE P comma n, and this is going to be the largest power of P less than or equal to n. And so this is basically just what I was describing, that we want to find how many times does a given prime divide 2n factorial, and how many times does it divide n factorial squared. Okay, so let's start with actually before we get into how we can evaluate this, I just want to make it a little bit more clear how we're going to use this to calculate our solution. And so I'm going to write out here this function, choose 2n comma n. That's just going to be equal to the product over p in primes, and it's going to be p raised to the power mult LTE p comma 2n factorial minus 2 times mult LTE p comma n factorial. You notice that this, I instead of writing or n factorial squared here, I just observed that any multiple of p that divides n factorial is going to divide n factorial squared twice. And so I just moved this 2 out here. So this is the explicit formula that we're going to be evaluating in order to solve our problem. And as I mentioned, this does turn out to be a little bit less direct than just writing out the full expression and doing the tedium of working out that division. But I think that there's some interesting mathematics in here, and so this is why I'm taking this route. Okay, so we need now a way to evaluate this mult LTE. Okay, so let's suppose we're trying to evaluate, mult LTE 2 comma 40 factorial. And so recall that this is just asking how many times does 2 divide into 40 factorial. That is, what power of 2 will divide 40 factorial evenly. Well, the first observation we can make is that every even number is divisible by 2. And so, 40 factorial is going to be, 40 times 39 times 38 times 37 times 36, etc. And we can, if we factor out the 2 from every even number, then we're going to end up with 2 to the 20th times, and then we're going to have 20 times 39 times 19 times 37 times 18 times 35, etc. And I'm not gonna go through writing out this whole thing for for every case like this. I'm just hoping that this will give you a sense of what I'm doing. So for every even number, we divide out a 2, and we see that 2 to the 20th must divide 40 factorial. So we're just going to make a note here. There are 20 even numbers. So, or even numbers less than or equal to 40. So 2 to the 20th divides 40 factorial. Now, even after we've divided out all of a 2 from every even number, you'll notice that there's still some multiples of 2 remaining. Like this 20 has a multiple of 2, this 18 has a multiple of 2, and in particular, any number that was originally divisible by 4 is still divisible by 2. And so then we can say there are 10 numbers divisible by 10 less than or equal to 40. So 2 to the 10th divides 40 factorial over 2 to the 20th. And we can continue this process. I'm going to start being a little bit more terse, but we can say that, so just to summarize what we have so far, if we have 20 divided by 2 is 10, that's 40 divided by 2 is 20. 40 divided by 4 is 10. 40 divided by 8 is equal to 5. 40 divided by 16 is equal to 2. Now, you'll notice I'm taking the floor here because we're counting multiples. So, 16 is less than 40, and 32 is less than 40. So there are 2 multiples of 16 less than 40. And then we have 40 divided by 32 is equal to 1. Okay, so what can we conclude from this? What can we conclude? And in particular, we can conclude that 2 to the 20th times 10th, plus 10 plus 5 plus 2 plus 1 divides 40 factorial. Okay. Let's see, that's equal to 2 to the 38? Yes, I believe I've done that correctly. So 2 to the 38 divides 40 factorial. Great. All right, so we can do a similar process for 20. So we have 20 divided by 2 equals 10. 20 divided by 4 equals 5. 20 divided by 8 equals 2. 20 divided by 16 equals 1. And so, therefore, 2 to the 18th divides 20 factorial. And now, this is the cool part. Now we can conclude 2, let's see, we'll say, and also, therefore, 2 raised to the 38 minus 2 times 18 divides choose 2n comma n. That is 2 squared divides choose 2n comma n. And in particular, 8 does not divide this number. Only 4 does. And so now we've taken care of the 2's. Now, at this point, you may be saying, okay, you said this was going to take a little bit longer than the tedious method, but this also seems fairly long and tedious. Don't worry, it's going to get easier faster. But we do have to slog through the 3's. Okay, so we're going to say 40 divided by 3 is going to give us 13. 40 divided by 9 is going to give us 4. 40 divided by 27 is going to give us 1. You can see already this is picking up pace. So we'll say 20 divided by 3 is equal to 6. Actually, let's just state our conclusion real quick here. So this means that 3 to the 18th divides 40 factorial. Okay, so then we'll say 20 divided by 9 is equal to 2. And that's it. 27 is greater than 20, so that doesn't matter. Okay, so then we'll say 3 raised to the 8th divides 20 factorial. And therefore, 3 raised to the 18th minus 2 times 2 times 8 divides choose 2n comma n. That is 3 squared divides choose 2n comma n. Great. Okay, on to the 5's. We're making progress. All right, so 40 divided by 5 is equal to 8. 40 divided by 25 is equal to 1. 20 divided by 5 is equal to 4. 20 divided by, well, it's not divisible by 25. And so we conclude, 5 to the 9th divides 40 factorial. And 5 to the 4th divides 20 factorial. And therefore, 5 raised to the 9 minus 2 times 4 divides choose 2n comma n. That is 5 divides choose 2n comma n. Okay. Now the 7's. 40 divided by 7 is equal to 5. And that's it. 7 squared does not divide 40. And so then we'll say 20 divided by 7 is equal to 2. Therefore, 7 raised to the 5 minus 2 times 2 is equal to 7 divides choose 2n, comma n. I'm becoming a little bit more brief in my comments here, since we've already done this process several times. Okay, now things start to get a little bit interesting. Moving on to 11, 40 divided by 11 is equal to 3. 20 divided by 11 is equal to 1. And actually, there will be several primes that are all of this form. So let's, actually just 2. So it's the case for both 11 and 13. So then 40 divided by 13 is equal to 3. 20 divided by 13. Excuse me, this is entirely wrong. I'm getting ahead of myself a little bit. And so let's just conclude, therefore, 11 to the, well, we can even be more succinct. We'll just say, therefore, 11 divides choose 2n, comma n. 3 minus 2 times 1 is 1, and so, yeah, we have this conclusion here. Okay, now we have 40 divided by 13 is equal to 3, and 20 divided by 13 is equal to 1. Oh, this is exactly what I was just saying. I don't know why I thought I had made a mistake. Therefore, 13 divides choose 2n. All right, and moving on, 40 divided by 17 is equal to 2. And 20 divided by 17 is equal to 1. Now, this is an interesting case. Both, and yes, this is, again, true for both 17 and 19. So, 19 is equal to 2. 20 divided by 19 is equal to 1. And that's because 2 minus 2 times 1 is equal to 0. And so 17 does not divide choose 2n, comma n, and 19 does not divide choose 2n, comma n. Okay, now you'll notice every prime bigger than 19 is not going to divide 20 factorial, which means that 23, 29, 31, and 37 all divide 2n, choose n. And now we are ready to assemble our solution. So going back up, you'll remember that we had 2 squared, 3 squared, times 5 times 7. So we'll say 2 squared times 3 squared times 5 times 7 times 11 times 13 and then times 23, 29, 31, 37. Now again, this was a little bit long and tedious, but I think the key thing that I think is a good takeaway from this process is determining the divisors of n factorial for some value of n. Using the technique that I'm describing here is a good tool to have in your toolbox. Okay, so now let's do 2 squared times 3 squared times 5 times 7 times 11 times 13 times 23 times 29 times 31 times 37. And that is our answer. Just to give you the satisfaction of seeing that we did do our math correctly, let's go back to the archive. And pull up the solution, and you'll see that it matches. So that video is a little bit longer than my typical videos. For those of you who stuck with it, I appreciate your viewership. I certainly had fun making this video. I hope you appreciated it, and in the next video we'll be continuing on with problem number 16.